you see that this is a projection. And you project the things here on symmetric spaces. And then I will not say much more about it, but it depends so much that we have all elements, so not just the upper triangular here. If you would be interested in upper triangular, we should take out, and this we do by some kind of pre and post multiplying this matrix here. So then we get a different expression. But this is the reason why higher moments become complicated, because always you cannot just factor it as a Kronecker product. You have always these two matrices which are involved. Even more complicated is the moments for the inverse Wishard. And I think I will end up by just showing you some interesting way to prove the result. But you can have higher moments. But to my knowledge, you can have the third moments, the Kronecker product of three moments. But higher moments are extremely complicated to obtain, and there's no nice expression as far as I know when you have a Kronecker product, because a Kronecker product, they collect all different combinations, or in fact you calculate too many of them. There's so many copies of this product, so one has to find some kind of minimal moments for this situation. But as you can see, the second moments here involves three matrices. And then there are more results. When you mix it with the inverse moments and the Wishard moments or a trace of this. So once you learn the technique, it's not so difficult to derive all these results. So now I want you, we have 3 minutes left, maybe very quickly. I defined a derivative here. And in this way, these are standard unit bases again, and here are partial derivatives. So they are organized in a special way. And then I have an epsilon here, which depends if I will have a copy of the elements or not here. So this is derivative, and in particular, it's one result that if you differentiate x with respect to x here, I will get this projection. Now, in order to derive the result, and I will use the Wishard density as a moment generating function. So here we have the Wishard density, and we know that if you differentiate a function and integrate, then you come to the border of the border of where the function is defined, and the border for the Wishard is 0, or when the determinant is 0 and everything is 0. So then we get some kind of multivariate partial integration relation of this type here. That if you differentiate the density with some element, it's equal to 0. So then we differentiate the Wishard density. And the Wishard density, you have the determinant here, and you have the trace which is a function of W. And then we differentiate it with W, and it should be 0. If you do it, we have to know how to differentiate the determinant here. And the determinant is given here by double the vectorized form of this W inverse times the determinant. So therefore we keep this expression here. And the same here. If we differentiate the exponent function, we just get the factor of sigma inverse of the vectorized form of sigma inverse and the density. And if you look at this expression here, you can see that we have the inverse here. And if you take what stands here is in fact the expectation of the W inverse times some constant. And here we have the half and half, and here this is, if we integrate this will equal to 1. And then from this relation, we can immediately say that the expectation of the inverse equals this expression. We can just cancel out the vector operation. So this is one interesting part. I will end up with, it takes maybe 1 minute more. an interesting phenomena,
Exactly.
and that is this
നാളത്തെ
any
ടോപ്പിക് അതാണ്
multivariate
ബ്രോ അല്ലേ? ഓക്കെ
distribution you can, or
Okay.
and which is invariant, or like a Wishart is invariant if you have special parameters, and from there you can get derived moments. But even beta and other,
No, I just
they have a
realized that
special
part of my
structure,
talks will be
and this
on
I want to try
MP1000,
to
which
explain
students would have
very
seen today.
quickly. So you have an arbitrary
Ah,
U,
ഷാലി പ്രസന്റ്
which is
another my recent
symmetric.
work
It has to be symmetric, but
that is
ദാറ്റ്
it's
ഈസ്
discuss the
rotational
cusp of
invariant,
data and
orthogonal
yes.
invariant.
Correct.
So if you pre or post multiply by gamma, you will have the same
Okay,
distribution.
professor.
And you know that if you know that that result, you can derive pretty
Segmentation.
many
ആണോ നമ്മൾ
results. So
പോരെ
here I see that this
എവിടാണോ
moment here should be of this form,
ഇവിടെ ഗൂഗിൾ ലൊക്കേഷൻ
equivalent, and then if you apply that it's symmetric, and then you apply that it's rotational
അങ്ങോട്ട്
invariant,
എടുക്കുന്നുണ്ട് ചുറ്റി
you
എടുക്കുന്നുണ്ട്
come up that this vector C has to be of this form when this is rotation invariant. And then you later choose
നോക്കണോ
different orthogonal matrices. So if you choose different orthogonal matrices, you can show that this relation holds if and only if you have that this is proportional to an identity. So the moment relation, what you're shown here now, was proportional to a constant identity,
അവിടെ
and
സ്ഥലം
this
ഉണ്ടായിരുന്നു അപ്പം
constant
കുറച്ച്
can be derived
ഇത്തിരി
through only
ടൈറ്റ്
one
ആണേലേ
element of U. Sometimes, if we would talk about Wishart or inverse Wishart, we would derive these elements through knowledge about
ബാറ്ററി റണ്ണിങ് ലോ
the
പ്രശ്നമാവോ
yeah, one element, the chi-square
ഇതിനകത്ത് കൂത്താൻ
distribution, in fact.
പറ്റില്ല
And you can see,
അവരെന്ന് സംസാരിക്കുന്നുണ്ടെങ്കിൽ ഇതായിപ്പോ
so here we have some general results. U is symmetric rotation invariant. It should be of this form. We know for a second moment, we know what the dispersion is. One doesn't know today for higher moments, but they are relations also. You can derive
ഫോൺ
relations just using this knowledge about rotational invariance. And as you can see here, yeah, there are three terms involved here for this. And this could be the
അല്ല
inverse
അവിടെ
Wishart,
വന്നേക്കുന്ന
for
വണ്ടികളാ
example. The inverse
അവിടെയും
Wishart,
കുറെ
we said that
അകത്ത് കയറ്റിയിട്ടുണ്ട്
the
അതൊന്നും
inverse Wishart was
കേരളത്തിൽ
C times identity. C was 1 over n minus p minus 1, which was derived, can be derived from chi-square variable. And here you can also find things which you can derive through chi-square variables. And
In
I think
200
my time
meters,
is over
at
now.
Compound Junction, take the
So
fifth exit.
I thank you for your attention. And it's a pity you cannot come with questions, or we can talk more in breaks and things like that. But all these
In
results here,
400
which I
meters,
have
turn
given
left
here,
at Overbridge
is an
Junction
old
onto
book what
LMS
a friend of
Hatakulamnara
me
Road,
and myself
Mahatma
wrote
Gandhi Road.
20 years ago, and Turner Color. And there you can find it. And you can just
അന്തവർഗീസിന്
and if you
ഇട്ടില്ലായിരുന്നു
need a copy of the book, you can just contact me.
ഫോർ സെയിം സെയിം
I can send the PDF
ഇല്ല
files
അയച്ചിരുന്നു
maybe. And
നോക്കാന്ന് പറഞ്ഞു
or
അബ്സ്ട്രാക്ട് ഒന്നും അയച്ചിട്ടില്ല മെയിലിൽ ഇട്ടിരുന്നു ഞാൻ ശ്രമിക്കാം
yeah, or you can
ഒന്നും തന്നൊന്നും
emails
എടാ
which are
ഇതാരാ
coming
യു
if
ഹാവ്
you need these results once,
ഓക്കെ
and I can try to help you,
നോട്ട് ഗോട്ട്
because I
എനി
can
മെയിൽ
imagine
റിലേറ്റഡ്
that
ടു
it must have
Okay.
been extremely difficult to follow
process of
what's going on here.
the final
But I
presentation.
hope that you get
Second
at
round,
least some ideas
the
what
result.
we can do with the normal distribution and with the Wishart distribution.
Two independent persons in order to construct what they are going to construct. Fine. So now we say let x then be x1 through x cube, same as before, lambda be lambda 1 through lambda cube, same as before. So the only difference between the JASA paper and Carlis and Melchizedek paper is that they are explicitly only limiting q to be j plus j choose 2. Instead of j plus j choose 2 plus j choose 3 plus etc. Right, e to the j. Instead of that, they are restricting to this number. And then they again define y equals ax. But a now has a very nice form that you will see. And what they are saying is let us think of this a Remember, y is j by 1, x is q by 1. So A is j by q. We are now looking for a j by q matrix A. And they said, let us consider A to have two parts. Partition A into two parts. A1 will correspond to the main effects in some sense, the first J, and A2 will correspond to the J choose 2 part. So A1 is now written as just I sub j, and I'll show you on the next page why this is. A1 is I sub j, it captures the main effects, and A2 captures the two-way covariance effects, and it is in j by, this is a long line. So let's just look at one example and then we'll come back to this. So very simple, ideas are very simple. So suppose j is 2, I just have a bivariate count vector and q is 3. Agree? 2 plus 2 choose 2. So then y1 and y2 are the two random variables that I observe. I'm going to write y1 as x1 plus x3 and y2 as x2 plus x3. x1 is a main effect corresponding to y1, x2 is a main effect corresponding to y2, and x3 is the common thing between the two and therefore induces dependence. Correct? So, everybody with me? As simple as that. And then look at A. A I said was a j by q, so here it has to be 2 by 3. In a 2 by 3 matrix, this first part is the A1. I told you it is the identity matrix because it is just taking y1 to x1, y2 to x2, etc. It's a map identity, right? So you get the identity matrix in this first part. And the second part, in this case, is 1 to 1 because we know how to do that. There is an x3 in the first equation, there is x3 in the second equation. So you all see why A looks like this. Any questions? So A is just your incidence matrix, right? So now, if I go back to the previous one, this sentence is essentially from the Carl's statement. A2 is a j by j minus 1 by 2 binary matrix, so zeros or ones. Each column of A2 has exactly 2 ones, j minus 2 zeros. So for example, let us look at another example where you will get a little bit more complexity. So when j is equal to 3, q is going to be 6. Agree? So y1 is x1 plus x4 plus x5. Each of the y variables must have a unique main effect. Agree? So y1 corresponds to x1, x2, x3. Then there must be dependence between y1, y2, y1, y3, y2, y3. Clearly, all of them must be dependent. Right? So we have x4 is common to y1 and y2. X5 is common to y1 and y3, x6. Everybody gets the idea? This is how these guys came up with this covariance structure. And now if you look at this A matrix, you will notice that this first j by j is an identity matrix. And then it said every column shall have 2 ones because you are relating to pairwise. So every column shall have 2 ones, which is what this is. And now you can go back and you can read this big sentence here. It makes sense. Okay? Everybody? So I think this was a very neat idea. Then once you have this structure, then what you should do is to split the parameter lambda also into 2 parts. So the first lambda will correspond to the main effects and the second lambda will correspond to the second order. And that is how they define their and then now let us look at the PMF in each case. Obviously, the reason we are doing all this is to calculate the PMF easily. So let us look at the PMF in this case. So now the joint PMF of y1, y2, given this q-dimensional parameter vector lambda, is nothing but, you just have to, this everybody knows, right? We do these kinds of things in our first math stat class. I'm giving you, in this case, I'm giving you 3 croissants independent. I'm asking you to form 2 new variables, y1, y2, right? You now have to rewrite the joint distribution of y1. Straightforward. That is all this. Okay? And you don't have this very complicated inverse mapping, product within inverse mapping and all that stuff, and this has been simplified. Same thing happens here. I wrote down the PMF, but the point is it starts getting a little bit more complicated, right? As the J dimension increases, it starts getting a little bit more complicated. And you see, this is where we were also struggling to do this fast for larger J. So there is a summation, right? Then this summation, once you get more complicated, and see the summation is over the three interaction variables, the three variables that contribute to the interaction. You have to sum them at set C. The set C is in, right? You want to read this thing. You can just see that it is getting complicated. That's all I'm saying. But all this is mathematically correct. Now, if all this is mathematically correct and Carles had done this, suppose somebody assigned you to do this calculation. What should you do? You should choose R, Python, whatever you want to choose, and you should start implementing this. And when you implement this, what will you do? Whenever you do a big problem, you first have to run one calculation for the PMF. You have to see how long is it taking. Let us say for j equals 2, it just ran like the wind. You didn't even have to worry. Then when j is equal to 3, it is taking like, let's say 10 seconds or 5 seconds, something like that. And then when j is 5 or 7, you are able to write this. There is actually a very nice recursive form also. I didn't write the form here because there's a very short amount of time. But these two guys, Carles and this other guy, in 2004, they proposed a recursive scheme. Only for j is 2 or 3. Because even for 3, doing it the direct way was time consuming. So they gave a recursive scheme. But when my student, Sean Hu, was trying to use that recursive scheme in their paper, it took a very, very long time. So in her thesis, Sean developed faster recursion. We implemented one small mathematical trick. And she made it a little bit faster than their recursive scheme. And this is in the thesis. Again, anything that I'm saying here, if anybody wants a paper or a copy or more discussion, you're welcome to reach out to me. What is happening is the computation of the PMF is directly depending on the magnitude of the counts. Obviously, if the count is small, let us say yi is just 3 or 4 or 5 or something like that, you're okay. But if what suddenly in a marketing problem, suddenly in one particular instance it is 38, then it goes to 65 and so on, then that is when the computation really slows down and you are in trouble. Okay, so and we computed the CPU time in seconds for the likelihood calculation of 10,000 simulated counts. There were 3 scenarios contributing to different lambdas. And so for example, if I take the univariate case when j is 1, we will simulate Poisson random variables under 3 scenarios. Lambda is 3, 5, and 10. That's what I'm saying here. We have different situations. Bivariate case, we are doing 3 scenarios. Trivariate case, 3 scenarios. But it's not as important as looking at this very quickly. Please take a look at so all you have to remember is scenario 3, the lambda is bigger. How about that? And in scenario 1, the lambda is small. So forget about even scenario 2. So you're going from a small count situation to a situation where the expected counts is rather large. Okay. Please look at how for trivariate Poisson is taking 248.788 seconds for that likelihood calculation. And those of you that are doing MLEs or Bayesian calculations and stuff based on the likelihood of the posterior distributions know that sometimes to get that the MLE, a converged value of the maximum likelihood estimate, you may have to run hundreds of thousands of times, right? You have to calculate the likelihood many times, and this is the stumbling block. You will be sitting, you will start your job, you go have a tea, you go have dinner, you will still no answer, you will sleep, you will get up, still no answer. That can be very distressing. In fact, the story is when I come to India, I'll tell you what the story is and how we got to that. Okay, is the story clear now? So we went from Mahamanulu to the Carless Meningsidau paper, and we looked at a recursive scheme. We looked at Shan's recursive scheme, and even for J equals 3, it is this big. So forget about looking at 93 districts in Tamil Nadu and all. That's it. You cannot do those kinds of things. Is everybody with me? So we do need a resolution to what one can do. But before I go to that, let me also tell you, I'm sorry, you should warn me about the time. What time should I call? You give me a warning.
Please 2:34.
So but now we can move because the idea has become clear, right? Now I can move a little bit faster. Now we are going to look at moments of the multivariate croissant. Why am I looking at it, and why am I saying what I am saying? I'm going to give you one example. Think about it and tell me whether multivariate croissant can help me. One of the problems where we applied this was in ecology. So one of the professors at UConn is an ecologist, and he goes to an island, Puerto Rico. He and his graduate students look at how many snails. You all know what snails are, right? How many snails of a particular type they can find. They go once in summer, once in winter. Okay, so they will say maybe there are 17 types of snails that they know about. So they'll all wear all those books and stuff, and they'll trek here and there, and they will try to write down, okay, type number 1, I found, type number 2, I found, and so on. And therefore, for every summer, winter, for about 14 years, they have the counts. Yeah. Now think about it. Some snails live higher up. Some snails live close to the ground. Some snails, 2 or 3 types of snails will live in a palm tree area, in a park. Other types, couple of them will eat the same leaves as food or something like that. So everybody is seeing what I'm saying. In some sense, where you live is the shared habitat. So if the counts of type 1 goes up, because there is a lot of palm trees, you expect that type 2 will also go up because they both like to live in that palm area. But now, type 2 and type 3 are eating the same leaf, let us say. Same something, whatever food they eat, I don't know. Suppose then there is a negative association, right? Because if more of type 2 is there, they eat up all the leaves, which means type 3 cannot exist and grow. So there must be a way in which positive associations must be explained and negative associations must be explained. In any problem, you cannot say, aha, I solved the multivariate computation, I'm done. No, you're not done. Because look at the conditional, the mean and variance is A times lambda. Lambda, remember, is positive value. A was an incidence matrix, 0, 1. Where am I getting negative anyway? So, if I assume that lambda is the mean and sigma is the diagonal of that thing, then the variance is positive. There is no way to get a negative covariance in the off diagonals. That is a huge shortcoming. Now, people who like to work with mixture distributions, now is your chance to say, okay, if a norm distribution, right, cannot have, I shouldn't say normal for the various, but let's just do this. Let's just do this. This 2007 paper, JSPI, they said, let us mix multivariate bosons. If I mix 2 or more multivariate bosons, then I can get the negative and positive associations. So let us just quick look at this. So let us mix H multivariate bosons. At this time, I'm not even saying I don't know H. Even H equals 2 is enough. Because I'm only doing this to bring in negative and positive correlations minimally. But then in a real data problem, you have to select H also. How many of these must I mix? That becomes another question, but we won't get into that today. So the mixing proportions, everybody knows mixture distributions? Finite mixture. So I have F1, F2, etc. H are different densities, right? And then I can mix them in proportions pi 1, pi 2, pi 3, pi h. Right? So that is all we are doing here. I am taking a multivariate Poisson distribution, another one, h times. I'm taking h multivariate Poissons, which are the Carless Metz-Dow multivariate two-way structure. Then I'm mixing them in proportions pi 1, pi 2, pi h. This has this PMF. Mixture PMF is very easy to do, but not easy to calculate. So how many of you are Bayesians here? Does anybody do Bayesian work? You do Bayesian? So talk to me about how you can calculate a mixture PMF when I do calculations. You've heard of Diebold-Roberts? You have to invoke Diebold-Roberts. Otherwise, this is a mess to calculate. Anyway, okay, so this is the answer to negative and positive associations. So at this point, we are okay. And as long as you're doing 2 or 3 dimensions, this can go. But if you go beyond that, then you are in trouble. So I'm just showing you how, in this particular case, the covariance, you see, this is just math stat again. This will be the covariance and it has this negative sign in it. And because of that, you have possibility of handling negative and positive associations. Okay, I only have a few more minutes. So I'm going to take this because of time. This is just I'm not interested in this. Okay. Let me stop here. Okay. So what I'm saying is the few pages I had there were just to show you how I can use that for some time series calculations. But we have determined that it is going to be very slow, so I don't want to waste your time with that. What people have been doing is, in order to speed up all of these things for time series calculations, Mike West is a very, very famous time series professor at Duke University. He proposed an idea for dynamic generalized linear models. Everybody knows GLM, right? Generalized linear models for count data modeling. So we are going to do dynamic. Then there's another one using copula modeling. Because remember, dependence. So I would have expected somebody to say, how about using copulas? So people have used copulas, but I am going to talk about this latent level correlation model because I promised Professor Satish, that I will talk about distributions only. We have done other things as well, but I'm going to keep my talk to how to leverage different distributions in the model. So this is a paper, this was one of my students, so we did this. Then Balaji is in Mumbai, he was one of our collaborators and we have a whole book. If anybody is interested in this last one, please let me know because there is a free version available. The whole book is available for free. I can give you the link and you can go and use any of these methods that you want. Okay, so I'll do this and then I'll stop. So this is going to be for time series now. I'll just talk in the context of time series. What does that mean? I told you summer, winter, for 10 or 14 years they are collecting the data. So you have counts over time for about 17 snails. Now, if you like a different domain, imagine something in your domain for this. Here is what I am going to do. I'm going to set up a setup where I allow different component count distributions. So for the let us say one of the snails is the most prominent snail. Very, very. Then the second one is less. Third one. And then the 17th one hardly any. Very scarce. Now, remember, you cannot use, you should, I'm not saying you cannot use, but generally if you have zero inflation, we will try to use a negative binomial distribution or a zero inflated Poisson or one of the hurdles, something like that, right? In the multivariate Poisson, think about it, even though you have a dependent distribution, everything has a Poisson characteristic. There is no zero inflation possible there. There is a guy called Teacher who defined a multivariate zero inflated Poisson. But how nice it will be if one of the snails can be Poisson, one of them can be negative binomial, one of them can be zero inflated Poisson, depending on its own nature. That is what I mean by saying I can allow for different component count distributions. Each component can be a different distribution that you like. And the second one is, instead of viewing, there's only one Bayesian, so I don't have to stress this, but we did this in a Bayesian framework, and exact Bayesian becomes very, very hard even here. So we did something called an approximate Bayesian. So all of you can kind of ignore the second bullet. Let's just focus on the first one. So once again, I have data. Now instead of just Y, I'm saying I comma T. T is time, summer, winter, summer, winter. I is location. There were about 66 locations in Puerto Rico. Now you can do spatial temporal if you want with this data on counts. But anyway, we didn't do that. So YIT is the number of counts in the ith location time T of the 17 snails. So if I think of snails as the snail types, J is 70. I is about 66 or something, and the T will be 40 or 38. That is the data. Then we will write an observation equation where we are saying I'm going to model these guys, each component, J is the component. I will model each component conditionally as a univariate distribution of counts. Now it's enough, whatever we studied in MSc MathStat, that is enough. Because I'm only going to use Poisson negative binomial zip, etc. Fine? That's what I'm saying here. How many of you have heard of Conway-Maxwell Poisson? You guys heard of that? Look it up. A friend of mine who is now at NC State works on this. Not NC, NC State. Conway-Maxwell Poisson. It includes many of the other distributions as special cases. But if you're planning to do a thesis on this, don't, because it's notoriously difficult to calculate beyond univariate. Even bivariate, one has to sell our house to calculate the bivariate distribution.
Pseudo model. We can compare to pseudo model.
You can, certainly. So, beta are taking the dependence is there in my. I'm going to show you. Not yet. Theta is only handling the mean. The theta is just the, it's like the lambda, right? It's the underlying Poisson's, independent Poisson's mean. That's all. We still need to build a dependence, and I haven't shown you why. How? Because in the observation equation, I'm only looking at them one by one. That's all I'm saying. I'm saying marginally or conditionally, right? Not the conditionally, marginally. Given the thetas, the YJITs are conditionally independent. Poisson or did I not move? Yeah, sorry, I keep on doing this. Is everybody? No, the dependence has not been discussed yet. Yeah, but the important thing is I no longer need Mahamanulu, I no longer need Carles Melixidov because I've made them conditionally independent. On the right hand side is just our usual distributions. Any count distribution you want to use, you put there. Agree? Okay, this I'll come later. I'll just show you this. Why not? This is just to show you how you can put Poisson. or I can put zip was on zip. But I can, depends on that component. I can put whatever I want. I mean, I could have put other things, but I'm showing you that all these things are possible. Now I need to model the lambda. That is why I said it is like generalized linear model. In generalized linear model, what do? We model the parameter, isn't it? In that setup. So we model the theta via a suitable link. For counts, it's always log link, so no need to worry. So I am going to take the log of theta jit, and on the right hand side, you can put for example, I am putting the intercept. The intercept is different for different snails and different for different locations. Then I put a gamma jt. I should stop. Then I put a gamma jt because that is going to capture my time trend. Then I put all kinds of covariates. See the snail problem, what is the elevation, what is the slope, how many palm trees were there, how many types of vegetation were there, all of that was given as covariates. And then this one, here this answers your question. So this is a random variable. For those of us who have taken ANOVA models, I can think of alpha JIT as a time varying random effect. Just a random effect. This is a mixed effects. This is a mixed effects setup. Because I have some fixed effects and I have some random effects. Alpha JIT is a response type time subject specific level correlated error. It's really a random effect component. I can assume that this is normal 0 sigma I, or I can do normal 0 sigma. See, model stuff you can do whatever you want depending on how rich or how compact you want. The most important thing is from a distribution point of view. If I really am focusing on distributions in this talk, I am saying I am allowing you not to use a complicated multivariate distribution only for capturing the dependence. Instead, let us simplify the problem by conditionally allowing for univariate first level. Yes, then bring in the dependence at the second level. At the second level, we bring in the dependence through this time varying random. That is the main distributional story. Everything else is things I did for my time surveys and other things. Yeah? And this is just a normal distribution that you are doing. Then, of course, I can put state equation. This is again a time series kind of thing. So you don't have to worry too much about this part. And we can modify a lot of things here depending on what we want. Since this has not become, since the Bayesian audience is very, very few, is it okay if I just skip this and you and I can talk if you want? Okay. So all these pages are saying is that after I do what I did, I can also bring in another level of speed if I'm doing Bayesian calculations by not working with the exact Bayesian inference, but rather making an approximation of the posterior distribution. But that is, I guess, people will not appreciate this here because if you're not engaged in Bayesian, then this may not work. So let's skip these Bayesian parts. This is the book I talked about. In case people are interested, you can use this. And then I just finished with one example. We used RNLab. Let me just say that we used approximate Bayesian using RNLab. Anybody who wants to learn more about that, or you would like to talk to me about RNLab, what is it? I'm very happy to. Anybody can email me, no problem. So in a financial application, anybody interested in finance as an application here? Yeah? No? So what applications are you guys interested in? Nobody is talking. I'm the only one talking. At least this guy nods to me, so I'm happy. Also, the students, what examples, what kind of domains do you work in as data? Nobody is interested in finance? stock market data. No? Very interesting. It's quite rich. And the reason I'm showing you this is because I want to show you how, even though you think stock market means price and therefore real value, I'm constructing count from that data. That's one of the reasons I wanted to pull this out and show you, because the data is not coming to me as a count. Snails came to me as a count, right? You're counting how many snails. But this is not that. So let us take a quick look at this and then I'll stop. Okay. Let me show you the next page. Let's start here and then you'll understand. So, stock market trades, right? Here you have Mumbai Stock Exchange. There we look at Nasdaq or the stock, S&P. So, we take the time within a day and we take 2-minute time intervals. Okay, 2 minutes, 2 minutes, 2 minutes each. And so we will get 195 such 2 minutes in the New York Stock Exchange. And then we will take transactions within a time interval, and then we look at the time, the price, and the returns. Everybody knows stock price and stock returns, right? So stock returns are nothing but the change in growth rate in prices. So we can calculate all this. But then here is how I'm going to define account. So what I'm doing is I'm going to set a threshold, some value tau greater than 0. Then we are saying the incidence of the IT log return. So I keep checking. T is 1 if the absolute log return is bigger than tau, 0 if it is less than or equal to tau. Then it is very easy to define counts. I am going to define YHT to be a high risk count, right? Which is the sum over all the transactions BIT. So I just count how many transactions with non-zero log returns go into the high risk group, because in absolute value they are larger than this value tau that I'm saying. So essentially we are taking prices and we are trying to high risk and low risk and counting how many high risks there are in a particular interval, how many low risks there are. Therefore, I have constructed a stock market data into bivariate counts, because high risk and low risk are bivariate counts. In my case, J is going to be equal to 2. So I am going to do all the things that I just as an example. So the reason I'm saying this is there are many young people here and we always say, oh my God, that is continuous data, that is positive value data. But depending on the context, you can set up and create an example for yourself that creates binary or counts or stuff like that. Always. It's possible. Of course, you have to understand the domain and talk to some domain people. Then, what time is it? I don't want to go. 5 more minutes. I can either show you. So if I took a particular stock, for example, on a particular day in this time window, 9:30 to 9:34, then these are the counts. And then high risk, low risk, and so on. Correct? And then I have some covariates and so on. So I have constructed count data. And I have constructed some covariates. So now I can go and implement level correlated. This is how some of these stock things will look like. So for example, the high risk counts are all in red and the low risk are all in green. The important thing to see is what? They are correlated. Because if they're absolutely independent of each other, then why am I bothering to do this model at all, right? But the plots like this, as you guys write your PhDs, you will start writing papers, and clearly it's very, very important. I'm also the editor-in-chief of a journal, so I know it's extremely important to catch the editor's attention. So sometimes we are all trained in math stat, right? I also studied in Chennai, so I was trained in math stat. So our first impulse is to keep on writing formulas and derive and proof and lemmas and stuff like that. Also, that is probably good. But unless in the very first introduction or even in the abstract, so an editor will read the abstract, they'll quickly look at the introduction, they will look at your data structure, wherever you give your data description, and very quickly what you are doing, your methodology and results. So it is very, very important to capture. So if I had not shown a figure like this, right, then the editor has no clue whether something is dependent or not. This appeared in actually one of our top journals, and that's why I'm saying this, because unless you make the effort and show lots of pictures and write about it and say, hey, from this picture you see things are dependent, therefore I want to do this. But then you could have done even Mahamanus maybe for this J equals 2. But we wanted to illustrate our Bayesian inla, so we did inla. Okay, so this is, and then we showed like this. Another picture in that paper is we took all this many stocks in the energy sector, and then we showed, look how correlated they are, the high risk and the low risk, the new variables that I am creating. Right, that is also very important because no journal these days likes very standard data, as you all maybe will realize. They are looking for something interesting, something novel, or something you are doing a little bit more different than what one would routinely think of doing with such data. I'm just giving you all these ideas because I see a lot of young people here. But anyway, this is probably not of much interest to you, but this is exactly how one of our models will look like for this particular data. This is the conditional independence. This is that second level with log lambda where I have this alpha JP, and this is my state evolution for the twin population. And below this, everything must be normal. In my level correlated model, there is one important thing, especially if you want to use INLA. Otherwise, no. This can be, the first level can be anything, any distribution. If it's in the exponential family, we are lucky, some calculations will be easier. But even if it is not in the exponential family, it's okay, we can manage. This portion is known as what is known as a Gaussian model. So this portion downwards must be Gaussian. Anyway, so these are again just the data analysis. I thought if I had time, I will show you, but I will share this paper if anybody is interested and you can look. But the point of showing you all this is mainly to also show young people how much information must be provided. Provide as much information as you can in a paper, provide very, very illustrative graphs. They can even be side-by-side box plots, but this is the association. So we are showing that the association between the high and the low risk, how they are different in the different sectors, and that they are definitely right away from zero. All those kinds of things must be shown. Okay. Just a lot of pictures. And this is about our paper itself. So this is not as important. I'll show you this in the next time. So let me just say thank you now.
Questions from audience?
If you all talk now, I hope you're talking about this and how you can implement.
Sure. Application.
How many of you think you would use something in the count area? There's a lot of data, right, that comes from the counts. How many of you are PhD students here? Just one? You're all master students? So they just forced you and dragged you to sit and listen to me. I'm curious, anybody, any young woman there, for example, is this likely to be of interest to you, either when you go take a job somewhere, or do you expect any of this to be useful or not really? No? Maybe next, are you all staying for my next talk also? You have no choice. Maybe I'll do what I do when I teach in my class. I'll ask questions. If nobody answers, I'll just put down the chalk and say, unless somebody talks, I'm not talking. There is no wrong question, right? None of you are curious about anything I said? No? It's like, I'm recently working on this kind of random effects estimation. I'm like, more about the large, right? Yeah. It's very fast.
Sorry, brief.
I'm trying to frighten them into talking. You can take a break.
Yeah. So a small thing, and after that, you join me for the next part. For 10 minutes, you can.
Children in various years. Very better understand. One says color, something is so different. Certain things what matter. Stand. Because it is a stand. Just as the first starts, people say, your own distraction and organize others. Then there is a training habit and writer like which means you have to that like you know so we said the kids just did whatever Illa allowed us to be. Very I say very distribution. You can give anything. Then you just have to work out all the calculations like things like that. These are complicated. So since for I tell students they should all sit in the same place every class, so I don't get student time falling on. Perfect. Not at all. Very nice. Thank you. Take an impression that I work in count data. I don't. These are just examples. I'm mainly a time series researcher, and I first want to talk about something called estimating functions. How many of you have taken advanced inference? Have you all, anybody taken? Have you come across estimating equations? I'm just going to play with you a little bit. How many of you have done maximum likelihood estimation? Everybody, right? Everybody knows how to maximize a likelihood. Is there an estimating equation when you maximize likelihood? Which are the estimating equations? When you do dl by d theta equal to 0, right? Is that an estimating equation? So there is a, I'll just tell you about this because if there are some of you that are interested in that. The only reason I didn't present that work here is because Professor Satish said this is distributions focused as the title, and that method is distribution free. So I wrote to Professor Satish and said, I would love to talk to your students about that, but it's a distribution free approach. So think about this. Suppose you want to do a likelihood, you want to do some modeling. And when you have to do a likelihood-based inference, what should you do? You should assign some probability distribution right in the beginning, right? In the first level, you should say something follows normal, something follows gamma, something like that. But what if you are not willing to do that? What if the gamma is a misspecification, for example, right? What in many situations, one of our own professors, has anybody heard the name V.P. Godambe? No? You guys should first learn history of statistics from India. How many of you know Professor C.R. Rao's name? Everybody knows Professor C.R. Rao? Yes. Who doesn't know C.R.? Hopefully nobody, right? So Professor Godambe was from Pune, and he created an alternate, what shall I say, to maximum likelihood. Some people today, like Chris Heidi in Columbia, started calling it quasi-likelihood. Instead of likelihood, they started calling it quasi-likelihood. So imagine that I do not want to say something is Poisson. Like using the first two moments or the first four moments of a distribution. I am willing to say the data is like a Poisson up to its first four moments. But beyond that, nobody knows, right? Because you need an infinite number of moments to characterize a distribution in general. Okay? So that is Godambe's estimating equations idea. And I really like it because even in the problems that I have shown you today in finance, we have a very nice paper where we are using, instead of using likelihood and posterior and everything in the fully parametric way, with distributions, in my model, I will have a model with parameters, but I will not have any error distribution. I will only have 2 moments, 4 moments. Anyway, the story is I wanted to first talk about that because I think for PhD students especially, that might be a nice avenue to think. If you're thinking of an alternative to the classical method. But in any case, I chose this because this is a distributions based thing. This is some work I was recently doing with some people from Brazil, and I think it has a lot of relevance to people who are looking at count data distributions. So you know my name and all. Some others take most for you. So I'll first talk about count data distributions, and then everyone has heard of zero inflated. Correct? We are going to talk about something called zero modified. And think about all the ramifications. This is really a distribution talk. This is not my kind of talk. I like doing the applied talks that you saw me give earlier, and much more applied than that. Then I'll talk about the zero modified power series distributions, which is the ZMPS distributions that my colleagues in Brazil have been promoting. So this is part of the work with Katyani. She's one of the first people who started talking about the ZMPS distribution, along with either her collaborator or her advisor, I'm not sure, Francisco Luzada from Brazil. Then Marinho is her husband who also works jointly, and Francisco is this person from the University of Sao Paulo in Brazil. And then Victor Lactose is my colleague at the University of Connecticut. So for a while, we have been thinking about these kinds of distributions and how to use them in some applications. And the application is something that you might all relate to because it deals with something that happened during COVID. And we were all collecting data and trying to see what kind of models best fit that kind of data. So again, lots of papers from a long time ago talking about distributions. I won't spend much time about this. So we can do Poisson, right? Everybody knows about the Poisson distribution. Basically, given these references, and people who are interested can pick up the slides. These are frequentist framework, Bayesian framework, all kinds of ways in which these are analyzed. But of course, we know if the variance is greater than or smaller than the mean, then you can have many, many flexible distributions, and there is also over dispersed data, under dispersed data. So there is this very nice survey type of paper, rather old, right? And so people are familiar with power series. Do we teach that? The power series family? Yeah. So power series family of distribution, which is rather a rich family. So once again, hundreds of papers this is the edited that book. Now, another encounter situation with count data involves discrepancies in the frequencies of zeros that we know. And for all, we all know zero inflation, zip distribution, everybody knows. And then it's a mixture, right? It's again a mixture distribution. Mixing what and what? A Poisson and a Bernoulli, correct? You mix a Poisson and a Bernoulli, and you can think of that as the zip distribution. And so for zero deflation can also occur in some situations. We don't usually think about that. obviously when you use the zip or when you use, remember when we do generalized linear modeling, when your professors teach you, yes, everybody, you learn GLIM, right? Maybe in your refresher class or maybe you start learning. So when you learn about generalized linear models, most of the software will automatically estimate the over-dispersion parameter, right, as what? The scale deviance divided by the degrees of freedom. So it's all very, very automatic. Whether you all use R or SAS or something. R. So I will just give this to you. And then usually when I teach that course, I teach applied statistics and I will say, okay, if you see that that is much bigger than 1, something like that, and then why don't you do the following? And then there will be a few remedies for over dispersion. Since you have many master students, I think have not yet taken that class, so you probably, but you will learn all of this, and they will say 2 or 3 remedies for over dispersion. And then I was teaching this data science class recently to some master students. And the data science students these days do not come traditionally like we all did from mathematics or statistics. Now we get students from engineering, some come from economics, computer science, etc. And one thing they are good at is asking questions without just accepting whatever we say. So one student in a homework, it turned out that scale deviance divided by degrees of freedom was 0.7. So that student correctly asked me, in your over dispersion remedies, you had remedies for over dispersion, but none for under dispersion, right? So like that, we don't focus on the under dispersion because that happens in very, very rare situations compared to over dispersion. Most of us but okay, the data is over dispersed, use negative binomial, do this, do that. Same thing. Zero inflation means what? When you count, right? You count if you look at the values assumed by the counts, and then you want to see whether that distribution looks like the histogram of a distribution when you generate from a Poisson with some lambda. Correct? So you try it. And it turns out that the e to the minus lambda, right, which is the probability of 0 under a Poisson, it's e to the minus lambda. Correct? When you want probability of 0 given that the random variable is Poisson. But even if you estimate lambda hat and you do e to the minus lambda hat, the number of zeros, the proportion of zeros in your data set will be much, much higher than that value. That is when we say it is zero inflation, and now remedy, nobody even thinks. Even an undergraduate knows that means go do zip. That's it. Everybody knows how to fit a zip in R. You use the zip data. But then there are situations where there can be deflation, meaning the proportion of zeros is actually smaller than what you assume under the Poisson, what you expect under the Poisson distribution. It can also occur in some situations. And in these situations also, if you ascribe a Poisson model, it is not correct because you will not be fitting and predicting correctly. And that is the region in which Tatiani and Moreno and people in Brazil, the people in Brazil are very, very strong distribution theory people. There is a strong group in Sao Paulo which is very good in these kinds of things. So anybody is looking for papers, look for papers out of the Sao Paulo school. You will find some very, very strong things. So for example, even as early as 1926, right, they studied the number of cancer cases in 2 suburbs. They in 2 suburbs. It's nice. Can you all see? I don't know if people in the back can see. Can you see this?
This way.
It won't move, right? Okay. So make it first. Okay. But can you all see? So anyway, here are a few examples. I don't have to read them for you. They basically, couple of places, things they found zero inflation was happening. So statistical modeling of zero inflated count data, we know. Here is a nice review. So now people started thinking pretty recently of zero deflation. And I explained to you what I think zero deflation is. And even though it is not very common, there is a need for that. The nice thing is, you know, when there is no need is if you write a paper and no journal will accept it. So far, these things have been accepted. So I'm assuming somebody is interested in learning about zero deflation. So zero modification means it can be either a zero inflation or a zero deflation. You do not have to know a priori what it is, but then you go and you can fit a zero modified distribution to the data, and depending upon how you estimate a parameter, you infer zero inflation. So zero modification is just a slightly broader thing than zero inflation. Correct? So that is what we mean. There is another paper that Tatiani and we have. It is still under revision, and so I didn't post it. It is on K modified. Everybody can understand what K modified is? Remember, Poisson distribution can take values 0, 1, 2, 3, etc. Correct? So it can be K for K equals 0, 1, 2, 3, etc. And we are saying here we've only been focusing mainly on the zero inflation, zero deflation, zero modification. But there may be situations, for some reason, there are some examples in our other paper where it can be a 5 modification. When you check the probability that y equals little y for a Poisson, okay, little y equals 0, 1, 2, 3, etc. I'm saying that 0, 1, 2, 3, 4 and all are consistent with the Poisson hypothesis, but 5 is not. So Tatiani said we can modify. So there is a way to check which K needs to be modified and then how to set up a PMF to do a K modified distribution. So that could be of interest to people depending on which domain you work. Okay. So when I say Conciacchio, I can never say her last name. So when you see that word, I'm going to say Tatiana. She's a friend that I work with on this. So they discussed zero modified power series distributions. So they took the general class of power series distributions and did zero modification. Therefore, very often a used example is a zero modified negative binomial distribution. And we have a full paper on that with an application which I will show you later. So these distributions, as I said earlier, can accommodate the discrepancy in the frequency of zeros without any previous knowledge. So a priori, I do not know what type of modification is necessary for this data. Is it more inflation, deflation? So as a special case in this paper, I illustrated the zero modified negative binomial, the ZMNB distribution, and then they obtain maximum likelihood estimates. Once you have the PMF really well written out and I can calculate the likelihood, I can do frequentist Bayesian, whatever. Okay, so let me first show you the ZMNB because it's a special case, and then we'll extend it to the form of the zero inflated. I mean, listen to the ideas. You don't necessarily have to take anything down because I can make the slides available to you, and if people need, I can leave it in the full paper as well. Yeah, I have all of the original papers plus the papers below. All right, so this is the one paper. It came out in computational statistics in 2022. This is joint work with Camille Marinho, myself, and Francis. Okay, so y is a random variable. Suppose it is 0, 1, 2, 3, etc. So let mean be mu greater than 0 and dispersion be phi greater than 0. It's called just the setup. Then if I think about the negative binomial distribution, we all know the form negative binomial distribution. Now, if I want to define the zero modified negative binary distribution, so let us just have the notation in mind. So if I write phi sub NB, I'm talking about the negative binomial, yeah, with parameters mu and phi. And of course, the random variable as well. But phi and b means negative binomial PMF, that is on equation 1. So now, if I want to define the zero modified negative binomial, right? So what is this? It's a mixture. It's a mixture. Mixture of what and what? This we know. I just told you what this is. Remember that this is a negative binomial PMF. So you're mixing a negative binomial PMF with probability P. And probability 1 minus P, the mixed is IY, which is an indicator function, which takes the value 1 if Y is 0. And otherwise it is 0, right? Everybody understands this mixing. That's it. So we are used to mixing, generally we mix F1 and F2, right? That's what we are used to doing when we do finite mixtures. But here we are thinking about this ZMNB, zero modification, as mixing a valid proper negative binomial density and an indicator, correct? Which indicates the presence of 0. Agree? Okay. Very similar to Bernoulli. Very similar to what we did in zip in some sense, right? Okay. So, oh, sorry. What is it? Now, there is a little bit of caveat here. Wait. The parameter P modifies the probabilities of the standard negative binomial distribution. Now, it satisfies this constraint. 0 is less than or equal to P less than or equal to 1 divided by 1 minus the negative binomial probability at y equal to 0. So if this is the max of the negative binomial for y greater than or equal to 1, correct? Because this is 1 minus the probability that the negative binomial is 0, right? Y is 0. Agree? Okay. Now 2 resembles a traditional mixture distribution, but it is different. P can assume values greater than 1, and that is what we talked about. So this was Francisco and Fagnani's ZMNB distribution. So they basically defined that this is the only page you need. And they said that this is not a typical mixture distribution. Then they defined the moments of this distribution. So you have mu sigma squared is mu times 1 plus p sigma. They are the mean and variance of the NB distribution. So if I don't put the suffix, I started putting NB and then it became very cumbersome. So if you just see mu and sigma squared, they are the standard negative binomial mean and variance. So then you can derive the mean of the zero modified distribution as P times Q, which from just a mixture form, right? So this is the variance and so on. Now, we can think of the proportion. I'm not saying that much difference. If you went to the original zip paper, for example, the one that was Lambert and somebody in technometrics, the same kind of thing would have happened. But here they are very careful because they are basically, we'll see where the differences come up. So now I can write what is the proportion of additional or missing zeros over and above what is available from the negative binomial, right? So this is all you have to do. Everybody agrees? Evaluate the pi under the ZMNB for y equal to 0 minus the pi under NB for y equals 0. That is the excess, 0 proportion. And that happens to be this value. So now if I put different values of the mixing proportion in 3, correct? Then I will get different cases of zero modified negative binomial distribution. I mean, to be honest, to me this is very boring because this reminds me of my classes in MSc or BSc that I took where I was learning all these distributions. But this I thought I would present this in case people become, I have something like this. So once again, in this, what I have in blue is nothing new. I'm just recalling to you what the ZMNB distribution is as a mixture form. So now we are going to try different values of P and then indicate what distribution it leads to, right? So this particular form, put P is equal to 0 first, then this left hand side will become just 1. So it's a degenerate distribution where the entire mass is at 0. Not very interesting really. Then when P is between 0 and 1, then this term will be bigger than 0. Right? 1 minus P times 1 minus that is bigger than 0. Therefore, the 0 modified probability of y equal to 0 will be bigger than the negative binomial version of this, and then we call it the 0 inflated negative binomial, right? Because under the ZMNB distribution, the probability of 0 is bigger than what we would expect under the negative binomial. Is everybody with me? So this is, so when P is between 0, when P is between 0 and 1, you get the 0 inflated negative binomial distribution, ZINB. Okay. Then when P is equal to 1, you get the standard negative binomial. When P is equal to different cases, right? I get more guidance. So anyway, so I just say that you guys can read this later on. All I will say is that in this particular form that you have for the ZMNB, by allowing P to take different values in the range that I specified earlier, you can generate or realize different types of distributions ranging all the way from the degenerate distribution to the standard negative binomial to the 0 inflated and then the 0 deflated. Everybody remembers that I said that you need not a priori go into a data analysis specifying anything. So now look at the estimated value of P. That is the point that I'm making here. Once you say that, okay, here is an R package that will do the 0 modified negative binomial distribution, and you take the data from COVID or something and you feed it into this R package, R function. All I'm saying is that P is an extra parameter in that call that you give to R, and I'm now showing you that different values of P tell you that you are in different zones. So if you estimated the value of P from your data to be between 0 and 1, then you will say this data is subject to 0 inflation. If on the other hand, you estimated the value and it was in this range, then you will say that this data was subject to 0 deflation. You might do many other things. You might segment your data and you might fit the model to different portions of your data, perhaps different times or different zones or whatever. And then you can say that while this particular segment is subject to 0 inflation, this particular segment is subject to 0 deflation, right? Lots of things can be done once you understand the range of P, what type of modification it leads to. The important thing is we do not have to fit a 0 inflated model. 0 inflated Poisson or a 0 inflated negative binomial you need not go to an R package and fit a 0 inflated model. You can fit Cartiani's 0 modified model, and the estimate of P that the data gives you will lead you to infer what type of modification happened. So in that sense, it's a very general way of fitting. Otherwise, what would you do? You will say fit a 0 inflated model. Then you will fit a 0 deflated model, right? Then maybe you will compare the AIC or something like that. And whichever gives me the smaller AIC, I will prefer that model or something like that. Here is my friend who is an expert in all of these kinds of distributions. I know. So the advantage of doing something like this, and Cartani has our packages or GitHub links with code, is that this is, I think, the best way one should proceed. You should not tie yourself down and then do model selection. Why? Why should I fit an inflated model, a deflated model, a degenerate model, a standard negative binomial model, and then model select between them? Instead, a single model fit with one additional parameter P is going to give us what we want at the end. That's the moral of the story. That's all real. Okay. And then we also have something called zero truncated negative binomial distribution. And then here they have in this paper, there is lots of figures like this. You can say in which region of the parameter space P can assume values, right? For different values of mu and different values of sigma. So those are the two negative binomial parameters. So various values of mu and sigma, they did some calculations and they plotted regions of P and people kind of plot. This is nothing more than what I just told you before. This is just a plot. Remember I said you have to catch the editor's eye. So plots like this are always nice to include instead of just showing formulas. So if you can think of this, adding plots like this, just to me, they're the same thing, but some people like. And then they define something called the index of dispersion. Now, the index of dispersion of a random variable we can define as variance of y divided by expectation of y. Looks like what? When we say sigma by mu, in our basic intro stats, we are taught something called sigma by mu, right? Mu by sigma is easy. That's how we standardize it. Take mu divided by sigma and standardizing. When you do sigma divided by mu is called the, who remembers? Maybe first year BSc. Maybe. Huh? Coefficient of variation. So here they are calling the index of dispersion to be the variance of the random variable divided by the mean of the random variable. And so this is posited in Katiani's papers as a measure of aggregation of disaggregation. So I of y can admit values bigger than 1 for over dispersed data, equal to 1 for equally dispersed data, than 1 for under dispersed. So this is something that is in their papers. So, right, so for example, I mean this is obvious, but let me just point out, just take the negative binomial is sigma squared divided by mu, because that was the variance and mu was the mean. Now sigma squared for the ZMNB distribution was mu times 1 plus p mu, which is bigger than mu, right? So for any value of p, so it will always be equal to that. Now for the ZMNB distribution, same thing. We already derived the, remember a few slides back, we looked at the mean and the variance. So we have the formula of the mean and the variance here. So you can define this index of dispersion for the ZMNB. So any distribution, once you write down the form and you have the variance and the mean, you can define this. And once again, it's a function of mu and p. Depending on those values, this IE can assume values less than or equal to 1 or greater than 1. So the contrast is that, again, just contrasting, as we all well know, the negative binomial distribution. Remember I said I always give 3 bullet points for my students. Okay, and Asha knows in our book we have it. So if it is over dispersed, don't use Poisson, use negative binomial, right? That's one of the things we say. And that is because of this formula that we all know, I think, that as long as you have a negative binomial distribution, this index of dispersion is always bigger than 1 because we know the variance is bigger than the mean. But the point is, the questions my students were asking, what if it is under dispersed map? So that's the answer. So you can use the ZMNB distribution because as you can use the yeah, you can use the ZMNB distribution because we are saying that the index of dispersion, depending on the values of mu and p, can be less than or equal to 1 or greater than 1, which means it could be under dispersed or over dispersed. Therefore, now I think an answer to my students will be, well, this group from Sao Paulo has a distribution called the zero modified distribution. So why don't you use that distribution if you want to be absolutely sure, right? But the problem is this. This has all been done so far for independent observations from a particular distribution. One should, of course, then take this and plug it into a regression model, which is what I will show. So you take the CMNB and try to build it into a regression model, build it into a time series model for the errors and so on, thereby ensuring that the underlying distribution allows for over and under dispersion, over and zero, under zero modification. Is that fine? So the model of all of this is that this CMND distribution is a flexible family which is suitable for getting to data from different fields of application without a priori specifying the type dispersion or the type of modification, because we know that it can support zero or zero inflation or zero deflation. We know that. Now I'm showing you by this index of dispersion that it can support zero over dispersion or under dispersion. So therefore, in that sense, it is flexible and therefore can be used, and you're only wasting one extra parameter p. Think about it. Oftentimes when we have to do these kinds of things, you grow your model very big, and then you will say, oh my god, so many extra parameters to estimate, why am I doing this? But you're doing all of this extra things that you're getting at the cost of one extra parameter estimation, which is p. And again, remember the range of p, the range of P will tell you which of those it would. Agree? So I'm just saying this is a very nice distribution, and that is one of the reasons we started working with this in trying to employ this in time series. We've done all the way up to stochastic volatility modeling with this kind of distribution. Okay, so this is just a plot again, as I showed you, to show the index of dispersion for different families. So just a few observations before I show you the power series family. So under dispersion of the ZMMB distribution exists when it is also zero deflate. That is just because of all those ranges of the parameters that I showed you. In the paper, we have some lemmas and stuff, but I didn't put all of those here. If anybody, like I said, if you want, I'm happy to share the paper. There, all the details are given. I'm just summarizing here. Okay, so in this particular case, under dispersion of this ZMNB distribution implies zero deflation, which we kind of show, which we argue. But the reverse is not true. So there are many points in the parameter space, mu, C, and P, for the ZMNB distribution, where it can be zero deflated and over dispersed. So one should not, I'm just saying, remember how sometimes you can take a parameter space, here it's three-dimensional, so it's a little bit harder, and you can partition the parameter space and say this happens here, this happens here. So all I'm saying is we have a few for lemmas or whatever to show that these things are all happening, and I'm showing you this. The smaller the dispersion parameter field of the negative binomial, the wider the interval in which mu can vary, permitting under dispersion in the ZMNB distribution. So these are just some characteristics of this distribution that I say. Now, I don't know how many of you have seen the hurdle version of these count distributions. It's like hurdle distributions. So it is useful to use the hurdle version because it helps us a little bit when we start doing multiplicative estimation and stuff. So let me show you what the hurdle version is. That ZMNB PMF. Once again, let's quickly take a look at it. The ZMNB PMF just means this. It means that the probability P requiring the negative binomial PMF and the probability 1 minus P will go to this I of y, which is an indicator function indicating y equal to c. Correct? Everybody remembers. This is the ZMNB PMF. And this is one way to write this. The hurdle version representation of the ZMMB distribution is this. So, I am going to write this as ZMMB 0. 0 means y equal to 0, right? Times number y. Adding and subtracting, that kind of stuff is going on here. Plus ZMMB y 1 minus I of y. So this is an identity. You can believe me that this is true. Then you just do a little bit of algebra, just grouping terms and so on. And then I'm going to write it in this form. Okay, doesn't matter. Let's just go. We believe we can do this. Then we are going to write omega as 1 minus phi n b 0 mu phi. So this is what? This is the probability that y is we get the equal to 1 in a negative binomial multiplied by p, and therefore you can write it as 1 minus omega times I of y plus omega times the zt and b. By the zt and b is a zero truncate. So all we are doing is we are writing the negative binomial zero modified as something that is involving a zero truncate, and that helps in the estimation. Okay. So this now becomes a proper mixture distribution. The original was not a proper mixture distribution. This is a proper mixture distribution. Why did I say the original was not a proper mixture distribution? Because p can assume values bigger than 1. But in this form, omega is lies between 0 and 1, which is what we want in a mixing. When we write a parametric, finite parametric mixture, we expect the sum of the pi's to be 1, right? And in the original case, that was not happening. When you write it in its Hurdle version, involving a zero truncated negative binomial, we indeed get a proper mixture distribution. And then that becomes easy when you start doing estimations. So that is the idea here. So this distribution expressed as a proper mixture distribution contains the zero truncated negative binomial as one of the mixers. Okay. I skip this. You can think of this as a superposition in two processes as well. So different values of omega lead to different things, modifications, same as before. So after all this, I'm going to say, remember what I said before, there was a degenerate distribution at 0, there is a zero inflated distribution, there is a zero traditional negative binomial, zero deflated, etc. The same kind of things you will realize. And it's like a one-to-one mapping. It's just that doing it this way has a proper interpretation as a mixture distribution, and then we use it in calculations. Okay, so they have discussed 3 real data examples to illustrate the versatility of this distribution. And the first one is something about how many possums there are in a particular area in Australia. Sure, those possums are those little creatures that run around. So this is what that data looked like. Yeah. And then from the fitted ZMNB. So remember I said you give data like this, you just use that fits the ZMNB distribution and estimate the parameters. So that's what this means. So I'm only going to concentrate on the P because that is what is going to help me decide which type of distribution I'm going to fall into. So it turns out that the confidence interval for P only contains values lower than 1. Okay, so now I have to go back to my original thing, right? Where I went from 0 to 1 means 0 inflate 0. So therefore, I infer that the data set is 0. That's what I said before. So it's as simple as this. Okay, so that means you infer the probability of not observing any possums is higher than the rate predicted by a traditional negative binomial. So in some sense, if you used a negative binomial model, you will be underestimating. That's the moral distribution. This is just independent data observation, higher data. The second one was European red mice on some apple leaves and so on. So there is a particular designed experiment they had, and then they went and observed the number of mice. And here is the data set, very simple stuff. Compared to the kinds of stock market and other things that I'm talking about, this is relatively straightforward. And in this case, the confidence interval for P includes the value 1. So that means there is no zero modification, which means in this particular case, you couldn't just choose the standard negative binomial distribution and it would be good. Doesn't mean you have to go back and fit. You want to fit. That's it. It's explaining. That's all. Yeah. So from this, whatever mu, phi, and all you estimate, that is what you will use. That is what you will use for predicting and stuff. And then the third example is some counting bacterial clusters in milk films. And once again, you have the data here, and this says it contains only values greater than 1. Greater than 1 means the data is 0. So that is what I meant as example. So now zero modified power distribution, I don't have to spend too much time because it's exactly parallel. I'm just going to tell you what the TS family is, then we're going to zero modify. And then we can talk about everything, but it's essentially the same idea. No new idea here. So this is a generalization of the ZMPS distribution. And this is, it is talked about in two papers. This is our joint paper. It just appeared in 2024 in ASTA. And then this is another new paper we have. This is an open journal. It's an MDPI journal. Generally, these journals are out of the reach for most of us because they ask you for a lot of money to publish in them, and so we steer clear of that. But then once you get some clarity, I guess they will write and say, okay, we'll let you publish for free, and that's how we said, okay, we'll publish it here. So these are two things. So again, the zero, okay, I think I said this, right? So this is a standard power series. I think I saw a lot of people nodding when I said power series family. So the power series family of distributions is very well known. It's there even in the original Johnson Brooks book and so on. So this is what the PMF looks like. It reminds you of the exponential family, some generic terms, and then you have to explain what those generic terms are and so on. So this is the general form of the power series family of distributions. A, F, and G are positive finite and quasi-differentiable functions, and then F has this expression where yes you can derive because obviously this should simplify. So well-known members of the power series family, Poisson, generalized Poisson, the Poisson that I mentioned, negative binomials are all members of the power series family. So all Katyani is doing is they are already done this with a negative binomial, so they are just doing it for a family. That's all. But the idea is exactly the same as I said. So there is no new idea here. So I can write the PMF like this. And so from the PMF of the power series family. So you can easily identify each member, the dimension, with what the corresponding FG and A are. Do that for the generalized Poisson, do it for the common Poisson, negative binomial and so on. So we can write down the same thing. Remember, this is kind of boring now because it's exactly the same path that I followed earlier. I'm showing you the moments of the power series distribution. Now they will be in terms of these functions. This is an equation everybody knows, right? If I want to take the derivative, I will just write f sub mu is dx by du and so on. Du and so on. So, and then, yeah, doesn't matter. So again, build the ZMPs. Like I said, if you had printed out the ZMNB, I'm just going to do exactly the same thing. So I'm going to build the ZMPs, and this is in her paper. I'm not involved in this. They have the ZMPS PMF, and they wrote it out like this. It's the same thing. Remember? It's the same thing. And the reason I have a Y is because YI is because instead of the system random variable we're talking about a random sample. That's what I'm taking a random sample, and then on each of those samples I'm doing exactly the same thing. Instead of the 5 ND, I now have 5 PUs. And then different values of yes, we'll see the same kind of thing. Zero inflation, zero deflation, zero standard policy. The same kinds of things can be done. It just becomes a little bit richer because now think about it. I told you that if you're doing a zero modified negative binomial, suppose it's an R function that does a zero modified right? And what did we do? At the cost of one extra parameter p, we just threw the data into that, and that told us in the negative binomial family, it stayed within the negative binomial family and told me whether I was inflated, deflated, dispersed, which way I was dispersed, and all that kind of stuff. Now, think about it. The power series family has a bunch of distributions and special cases, correct? So, it will be nice if there is an ARM package into which you can throw the data, and you don't have to be restricted to negative binomial. You can say, I want to think about inflation, deflation, dispersion, etc. in the context of the power series family, in which case you will say, okay, the best member that your data is pointing to is the composite, let's say, with T in this region. So you can say you want a zero inflated composite, something like that kind of thing. That's the idea. So extending it to a richer family means the authors, I hope they have it. I haven't checked because, like I said, this is not my area of research. What would be nice is people like us can just go use that function and fit data that we want, and we are doing it in the context of a bigger family of distributions and not just the negative binomial zero. That's all it is. Okay, but same thing. You can do all of these things and therefore identify where that P is, and depending on where that P is, it is this. And then I don't know how they select. Say the early model can be written. This is all talking about in which range what it is. That is all it is, over and over and over again, right? So this is modeling, regression models. So here is one setup with regression, and then I will stop. So regression, we have a response variable. The response variable is a count, right? Independent data, no time series, nothing, just independent regression type data. And then the exercise can be predictors. Yeah, so you can have different types of predictors that you want. And then you set up your predictor matrix, and here is your. I'm calling it data mu because this is a regression model for the mean. Now I'm also going to model the hurdle, the proportion. Remember, in zip modeling, that is what we will do. When you model regression using zip, we have to model the Poisson mean mu, and we have to model the Bernoulli proportion P. This is not very dissimilar. You're going to model the mean mu for the ZMPS, and we are going to model the omega, which comes from the hurdle part. And I like that. That is because we like that being a proper mixture. That's all. So we have separate parameters for the mu, separate parameters for the omega. If you went to the Lambert paper, you will see exactly the same kind of situation. And then people will say, why cannot I use the same predictor for mu and for B? You can. There are some papers who have done that, and some papers have put nothing. No predictors for the omega, just an intercept. You can do any number of things. This is just saying, suppose there is a bunch of predictors that explain the mean, use it there. There is a bunch of predictors that explain the mean, use that here if you want. Or you can use the same X in both places. Am I basically maybe I'm doing something. But if everybody understood the regression setup, that is what yeah. So that's all this is. Okay. So we can set up all this stuff. Let me end by showing you one quick application to COVID data. Okay. This is a sad data set, but I think Katyane was interested in doing this. I had no business in collecting this data. It was her data. They wanted to see femicide means killing of females, right? In our case, we all, for a long time in India, we were talking about infants, right? But here I think it is any age. So they got data from Sao Paulo, and then they used the Municipal Human Development Index as an explanatory variable. And I think this had to do with some kind of economic development that they collect, right? So higher values means higher development and lower values. So they collected this data for the COVID clinics, right? From 642 municipalities. And their analysis identified the zero modified binomial model as the best fit for the and they showed that there was inflation and so on. But I mean, the results are not as important. You can always go and read the results. But I'm basically saying that this is the framework that you need to use. You do need to model the mean, you do need to model the omegas, and you need to understand what the betas for each of them means. And that's what this paper was doing. There's tons of tables and all that I haven't shown you. So basically their conclusion was that the mean number of notification increases as the development index increases and is slightly higher during the pandemic. So the trend indicates that municipalities with higher levels of development tend to report a greater mean number of femicides. I don't know why that is, but that is what they report. Okay, so that's it. That's the story. And I don't know if this distribution speaks to you guys, but if the distribution speaks to you guys, feel free to reach out to Katyani. Don't write to me. I am not an authority on this. I was just a co-author because I was helping them do other stuff. I was not responsible for their distribution. That was all her contribution to the literature. Okay, thank you.
On behalf of the organizing committee and participants of CSDT 2024, I extend our sincere gratitude to Collecting News. Her clarity of presentation and express insight by the fire session of the conference which of the teaching on the Bible. We are grateful to her for sharing her valuable experience with us. We also find how things for our practical engagement about the workshop. Thank you. Now, I invite Professor Suresh Kumar to suggest now for gratitude to confirm our leadership.
I already know, so clarifications is very so, Madam is tomorrow, you can give tomorrow.
But the second one, I deferred all my questions to Katyani. No, I was kidding. You guys can write to me. I'm just saying that this is her baby that I was. You had a question? Oh, I think that makes sense. And all? No, what's going on? No way, right? Yeah. Let me check that.
Talk about for now.
Thank you. Right. Yeah. Yes. Check the, let's see, first please how. Here the tag, so pretty easy guys. Okay, that's everybody. For example, I'm saying this, which the not in me. It's have stuff, it's checks. And everybody will stand, starting to one paycheck for her. The spice and then we can clear the children.